logarithmic and exponential functions. And so the first question usually that I get or that's on your mind is, what is a log? A lot of times it's the first class that term is shown up in, unless you got really deep in a former algebra class, you may not have seen this. So I just want to just demystify it, and then we're not going to talk about it again until later on in the chapter. But here's the difference. If you were doing an exponent like 2 to the third, we normally think about that as working an exponent. 2 to the third means 2 times 2 times 2, which is 8. The answer to an exponent. When we're working a log type problem, we're trying to figure out the exponent needed to get that number. 2 to what power is 8? So doing a logarithm, or log for short, is finding the exponent needed to get to that number. So 2 to the third, the answer would be the 3, the exponent. Well, instead of writing it in this form, we write that as log base 2 of 8 equals what, or equals x. This is the way you'll see logarithm problems written, but it's really just something we have to get used to. It's really this statement just written in a different syntax, a different way, so that the answer is solved for it. Over here is the variable. So again, the base, which is kind of, you can think the basement of it, the lower subscripted area, that's the base of your log. So it's a base 2 log. The argument, or the answer to the exponent, would have been 8 equals what? The answer to a log, I want you to kind of think this through, write it on your hand or something, remember this. The answer to the log is the exponent. That's what we're solving for, the exponent. The answer to the log is that exponent needed to make this happen. So 2 to the third is 8. So the answer to that would be 8. On your calculator, you have a log button. If you hit log 100, and if you have your calculator, do that and just see what you get. You should get 2. Log 100 is 2, and that's because that basic calculator button is a base 10. 10 is understood if you don't have a different number labeled here. So this is understood to be a subscripted 10, so that means 10 to what power is 100, and that's why you say 2. So if you hit log of 1,000 on your calculator equals, you should get a 3, because 10 to the third is 1,000. The other log button that you have is the LN button. The LN button is the natural log. This is called a common log. LOG is the common logarithm, base 10. LN is the natural logarithm. And the base that's understood when you hit your LN button is E. Now E, I know it's a letter and all, but it actually stands for a specific value. So it's not a variable, it is a constant. It has a value. E is approximately 2.718. It's like pi. It doesn't stop, it just keeps going. It's irrational E, just like pi was irrational. So Ln means we're talking about E. So if we did Ln of E, that would mean E to what power is E? So what do you think that's going to be? E to what power would be 1. And you can type that on your calculator. Ln E equals, come out with 1. And so if we were doing Ln of something else, like Ln of 7, for example, this one's not going to come out as perfectly. But your calculator is calculating E to what power is 7. So go ahead and get that if you will. So 2.718 approximately to what power would be 7? What'd somebody get? 1.9? About 1.9? So that seems reasonable. Say E was 3. 3 to the second would be 9. I mean, that would be an estimate. E is a little less than 3. It's 2.7 something. Raised to that power should equal 7. All right, so that's the meaning of the log, and we'll come back to that in a later lesson. Our lesson starts out in chapter 4 with what an inverse is. And the reason is logs and exponents are inverses of one another. They undo the other one, you could say. The x and y kind of switch places where you're solving a different spot in the equation. So logs and exponents, they're really very related, right? They're the same thing. Kind of like add and subtract are related. add and subtract, undo each other. Multiply and divide are related. They're inverse operations of each other. It's the same idea. They're different ways of expressing, like subtracting is adding the opposite. So adding is definitely related in with subtracting. So same thing is true with exponents and logs. They're just different expressions of the same sort of idea, powers. Just so you know, an application we're going to talk about later, if I get to it in 4.2, is compounding. The E, that E power or E base that I talked about earlier is going to show up in this little formula. The continuous compounding formula says that, say you put in a base amount, P, like principal, if you were doing an interest problem, that would be your starting amount, how much principal you put in. We're thinking money. And then A would be how much that money grows to. So we could do a continuous compounding, uses the E base, kind of like pi shows up in the circle, E shows up in some business applications and some science applications. But anyway, it's called the PERT formula. The starting value, P, times E raised to the rate of interest or the rate of whatever you're doing, times time, how long you leave it in there, will show how much something grows to. So there's the PERT formula whenever it's continuous compounding. The other formula we're going to use is incremental compounding, when it's compounded monthly or compounded semi-annually or daily or quarterly, some increment of time that you can measure. You're going to use this formula. So your money or whatever it is that you're growing, your population grows to this A amount equals P, that's the starting amount, times 1 plus the rate of growth or decay divided by N. N is how many times it's compounded per year. So if it's compounded monthly, we'll put a 12 there. If it's compounded quarterly, 4 times a year, 4, and so on and so forth. So N is how many times per year, then raised to the power, use that N value again, times T. So an example I have for you, just an application where we're going to need to solve logs. I wanted to show you, this is where we're leading up to at the end of the chapter. We want to be able to solve a half-life problem. So here's a problem where you had 40, let's say, grams of something. Every semester I say this. I need to find out how much a McDonald's hamburger actually weighs and talk about deterioration rates and stuff, but I don't have a good, perfect application for you, so just go with me. Let's say you have a 40-gram hamburger, and we want to know how long it will take it to deteriorate to only 20 grams of hamburger, right? It will eventually deteriorate and rot away, decompose. So it's deteriorating. So its rate is negative. It's a negative growth rate. So I'm going to say negative 0.03 is and that will be given to you in the problem. You're not expected to know these percentages. So that will be shown to you, given to you. And then we're trying to figure out how long will it take that hamburger at that rate of decay to be half of itself. That's a half-life, when something decays away. So because we would be solving for the exponent, we consider that working a logarithm problem. And we'll use the principle of logs to figure out what that t-value is. Same thing for this equation. This one I was thinking money. We put $10,000 in the bank, that's your starting amount, your p-value, and we want it to grow. This time it's a positive rate. We want it to grow to $20,000. So let's say you're getting 2% interest, which would be high at this economy. So 2% interest, 0.02, a positive rate of growth. Compounding it monthly, so I said divided by 12, raised to the 12, which is the n value used again as an exponent, times t. T is how many years you let the money stay there. So I know you're curious to know this, but this is what we're working into to see how long it would take $10,000 to grow into $20,000. And to solve that problem, I would need to use the logarithm principles. Anytime I'm solving for the exponent, if the exponent is a variable, that's doing a logarithm. You're solving a logarithm. Now, some problems like 2 to what power equals 4, you can kind of figure it out without having to solve with logarithm rules. So we would say 2 to what power, and I could call that 2 to the second. If you can make the bases the same, the exponents will be equal. So x actually, you can say equals 2. So you'll have some problems in your homework like that. Let's say we said 3 to the x minus 1 power equals 9 to the x plus 2, let's say 2x plus 2. To solve that, again, we will solve that at the end of the chapter with logarithms, but since these can be made to look like like bases, we won't have to do it that way. We can get like bases of 3. 9 is 3 to the second, and then bring down its exponent. So if you can make the bases look the same, then you can kind of mark out the bases and set the exponents equal to one another, and then solve that for x. So that, I'm kind of ahead of myself. That's actually in 4.2, but I've kind of got off on a tangent there. So let me pull back now, and we'll come back to that. Back to the beginning, 4.1. So if you found that in your note packet, I really just wanted to start you off with knowing what a log is, just a frame of reference for that, and knowing that logs and exponents are inverses of one another. Okay, so that's what it says.